This is the belief state space for the centralist acting problem. So we started off here. We drew the circle around this belief state. We don't know anything about where we are. But the amazing thing is, if we execute actions, we can gain knowledge about the world, even without sensing. So let's say we move right, then we'll know we're in the right-hand location. Either we were in the left, and we moved right and arrived there, or we were in the right to begin with, and we bumped against the wall and stayed there. So now we end up in this state. We now know more about the world. We're down to 4 possibilities rather than 8, even though we haven't observed anything. And now note something interesting, that in the real world, the operations of going left and going right are inverses of each other. But in the belief state world, going right and going left are not inverses. If we go right and then we go left, we don't end up back where we were in a state of total uncertainty. Rather, going left takes us over here, where we still know we're in one of 4 states rather than in one of 8 states. Note that it's possible to form a plan that reaches a goal without ever observing the world. Plans like that are called conformant plans. For example, if the goal is to be in a clean location, all we have to do is suck. So we go from one of these 8 states to one of these 4 states, and in every one of those 4, we're in a clean location. We don't know which of the 4 we're in, but we know we've achieved the goal. It's also possible to arrive at a completely known state. For example, we start here, we go left, we suck up the dirt there, we go right, and suck up the dirt. Now we're down to a belief state consisting of one single state. That is, we know exactly where we are. Here's a question for you. How do I get from the state where I know my current square is clean, but know nothing else, to the belief state where I know that I'm in the right-hand side location and that location is clean? What I want you to do is click on the sequence of actions, left, right, or suck, that will take us from that start to that goal. And the answer is that the state of knowing that your current square is clean corresponds to this state, this belief state with 4 possible world states. And then if I then execute the right action followed by the suck action, then I end up in this belief state, and that satisfies the goal. I know I'm in the right-hand side location, and I know that location is clean. We've been considering sensorless planning in a deterministic world. Now I want to turn our attention to partially observable planning, but still in a deterministic world. Suppose we have what's called local sensing. That is, our vacuum can see what location it is in, and it can see what's going on in the current location. That is, whether there's dirt in the current location or not. But it can't see anything about whether there's dirt in any other location. So here's a partial diagram of the part of the belief state from that world. And I wanted to show how the belief state unfolds as 2 things happen. First, as we take action, so we start in this state, and we take the action of going right. And in this case, we still go from 2 world states in our belief state to 2 new ones. But then, after we do an action, we do an observation. We have the act-percept cycle. And now, once we get the observation, we can split that world. We can split our belief state to say, if we observe that we're in location B and it's dirty, then we know we're in this belief state here, which happens to have exactly 1 world state in it. And if we observe that we're clean, then we know that we're in this state, which also has exactly 1 in it. Now, what does the act-observe cycle do to the sizes of the belief states? Well, in a deterministic world, each of the individual world states within a belief state maps into exactly 1 other one. That's what we mean by deterministic. And so that means the size of the belief state will either stay the same, or it might decrease if 2 of the actions sort of accidentally end up bringing you to the same place. On the other hand, the observation works in kind of the opposite way. When we observe the world, what we're doing is we're taking the current belief state and partitioning it up into pieces. Observations alone can't introduce a new state, a new world state, into the belief state. All they can do is say, some of them go here, and some of them go here. Now, it may be that for some observation, all the belief states go into one bin, and so we make an observation and we don't learn anything new, but at least the observation can't make us more confused than we were before the observation. Now let's move on to stochastic environments. Let's consider a robot that has slippery wheels, so that sometimes when you make a movement, a left or a right action, the wheels slip and you stay in the same location. And sometimes they work and you arrive where you expected to go. And let's assume that the suck action always works perfectly. Now we get a belief state space that looks something like this. And notice that the results of actions will often result in a belief state that's larger than it was before. That is, the action will increase uncertainty because we don't know what the result of the action is going to be. And so here, for each of the individual world states belonging to a belief state, we have multiple outcomes for the action. And that's what stochastic means. And so we end up with a larger belief state here. But in terms of the observation, the same thing holds as in the deterministic world. The observation partitions the belief state into smaller belief states. So in a stochastic, partially observable environment, the actions tend to increase uncertainty, and the observations tend to bring that uncertainty back down. Now, how would we do planning in this type of environment? Well, I haven't told you yet, so you won't know the answer for sure, but I want you to try to figure it out anyways, even if you might get the answer wrong. So imagine I had the whole belief state, from which I've diagrammed just a little bit here, and I wanted to know how to get from this belief state to one in which all squares are clean. So I'm going to give you some possible plans, and I want you to tell me whether you think each of these plans will always work, maybe sometimes work, depending on how the stochasticity works out. And so here are the possible plans. Remember, I'm starting here, and I want to know how to get to a belief state in which all the squares are clean. And one possibility is suck, right, and suck. One is right, suck, left, suck. One is suck, right, right, suck. And the other is suck, right, suck, right, suck. So some of these actions might take you out of this little belief state here, but just use what you knew from the previous definition of the state space and the results of each of those actions, and the fact that the right and left actions are non-deterministic, and tell me which of these you think will always achieve the goal, or will maybe achieve the goal. And then I want you to also answer for the fill-in-the-blank plan. That is there some plan, some ideal plan, which always or maybe achieves the goal? And the answer is that any plan that would work in the deterministic world might work in the stochastic world if everything works out okay. And all of these plans meet that criteria. But no finite plan is guaranteed to always work, because a successful plan has to include at least one move action. And if we try a move action a finite number of times, each of those times the wheels might slip and it won't move. And so we can never be guaranteed to achieve the goal with a finite sequence of actions. Now, what about an infinite sequence of actions? Well, we can't represent that in the language we have so far, where a plan is a linear sequence. But we can introduce a new notion of plan in which we do have infinite sequences.